My name is Catherine Deverin, and this is Lab 3. The purpose of this lab was to find the distance dependence of the magnetic field due to a bar magnet by first measuring it directly using our phones and then predicting it with a computational model. We could apply the Biot-Savart law to determine the relationship between the distance and the magnitude of the magnetic field, finding it for both the on and off axis magnetic fields. Since Earth is a magnetic dipole, we needed to place the bar magnet's magnetic field so that it would be perpendicular to the Earth's field along the north-south axis. Another fundamental principle used was the Biot-Savart law for a magnetic field on and off axis, as shown in red. We also used the linearized form of the distance dependence equation for the magnetic field to calculate the on-axis magnetic field. For the results of the experiment, I calculated both n, the distance dependence factor, and mu, the magnetic dipole moment, as well as the net magnetic field at a 45-degree angle, both experimentally and computationally, with the value shown on the screen. To calculate the on-axis magnetic field, I first compensated for Earth's magnetic north-south axis and oriented the meter stick and the bar magnet orthogonal to this axis, so that I'd only be measuring the magnet's magnetic field. I then located the magnetometer chip on my iPhone for accuracy. I then recorded distances of my smartphone from the bar magnet, at which it read different BX values on the app I used, repeating 3 times for each distance for accuracy. In measuring these, I found that when the magnetometer was far from the magnet, there was a near zero magnetic field in the x direction, but the x component of this magnetic field increases as the magnetometer moves closer to the magnet. This represents my results from the first part of the experiment, with the distances and corresponding x component of the magnetic field listed in the table. These results combine to form a graph as shown on the left, with the equation representing this line as shown in the blue highlighted. The equation for the line on the previous slide allowed me to solve for n and k, which then allowed me to set the two equations I knew for B, the magnetic field of the bar, equal to each other. This way I could solve for mu and get a value of 3.18 amps times meter squared, which is the magnitude of the magnetic moment. Next, we wanted to find the off-axis magnetic field experimentally. So I first moved my phone a distance dperp until B net would equal 100 microtesla, as shown on the image on the right. I recorded the y component of Earth's magnetic field so that I could adjust the final y component to account for this, and then recorded the magnetic field's components at this 45-degree angle. This table represents my results for the off-axis magnetic field, where I found that at an average distance of 0.284 meters, the average vector for B produced at a 45-degree angle is as shown on the bottom of the screen, with a magnitude of 4.8 times 10 to the negative 5 teslas. To solve for the magnetic field computationally, I first found the magnetic field on the axis by using the code for the magnetic moment and the magnetic field. I then did the same thing to plot 4 arrows representing the field perpendicular to the axis, just using R-perp and B-perp instead of R-axis and B-axis. My final model represents the magnetic field produced by a bar magnet, with the 2 orange arrows representing the on-axis magnetic field, the 4 blue arrows representing the perpendicular axis magnetic field, and the purple arrow representing the magnetic field 45 degrees from the axis. This final result had a magnitude of 2.189 times 10 to the negative 5 Tesla. The experimental magnetic field I calculated was more than double the magnitude of the computational magnetic field. These differences could be due to human error with my own setup of my phone and the use of the app, which could have resulted in the differences I saw in the vectors for their respective magnetic fields. If we hadn't oriented our experiment to compensate for magnetic north, then the results would have also included the Earth's magnetic field, rather than just the magnetic field due to the bar magnet, which would have made the results inaccurate and different from what we found in this experiment. If we were to stick 2 identical magnets together end to end and run this experiment again, then there would be a greater magnetic force associated with this, so the measurements gathered would be greater in value, almost but not quite double in value.